team members contributed to this, and half of them are in this room. You can see these names again. This cartoon was just to remind me to explain what the cold classicals are and why I'm interested in them. If you imagine a nebular disk with some compositional gradients occurring with heliocentric distance and maybe some size distribution gradients as well, and eventually Neptune throws everything all around, the cold classicals are these red ones that are more or less still where they formed, and so you have maybe the best hope of trying to use those to tie back to the gradients in the nebula because they're still more or less where they started. Unlike the hot population, it's kind of all over the place, and you have to work a little harder to figure out where they came from. All right, and then what triggered this was ASIAA, the horizons encounter, when we saw this methanol ice, and compared to the other objects that at the time we had also seen methanol ice on, which have water ice bands. ASIAA really didn't show much sign of the water ice band, and that was kind of a head scratcher because water is harder to get rid of than methanol. It's harder to radiolytically destroy, it's harder to sputter away, and so what's up? Is it that these objects formed out beyond the CO line where carbon monoxide ice can do hydrogen addition fairly readily, or are they, as explained in these kind of nebular models, where the hatched area is where carbon monoxide is frozen, and the blue region is where methanol is the main carbon carrier. Or even is the methanol inherited from the giant molecular cloud even before it collapsed on the disk, and some of those could be true. So what we wanted to do was collect a bunch of cold classical targets and see if they look like ASIAA or see if they show any trends. And of course, the DISCO survey that you've already heard a fair bit about got 5 cold classicals, but you notice that the H magnitudes are fairly small, corresponding to very large objects in the 100-kilometer range or larger. So what we did was we added 9 more targets, and you may say this guy can't count, but that's because a bunch of these are duplicated, because the first group basically holds the distance constant about ASIAA's distance, and you'll notice that 4 of the DISCO ones do as well, but varies the H magnitude, so we get a chance to see if there's a size-dependent effect. And then the next group holds the H magnitude constant and varies the heliocentric distance, so we get a chance to separate out whether there's a size-dependent effect or a heliocentric formation distance effect. All right, and graphically, this just shows those 2 slices, and of course there's uncertainties on the absolute magnitude, so these, you don't really talk about have error bars on them, but we can always just do more photometry and actually tie those down. And the open symbols are not yet observed, so I've got a fairly weak sample in this axis to show you, but I have a pretty good sample in this axis to show you. All right, so spectra, and this was just the part where I preferred not to have people digesting these just quite yet, because I'm only just starting to digest them. And a few things to see here. So first, at the long wavelength end, the signal to noise is pretty crappy. These are fairly small, distant objects and require a fair bit of exposure time. I'm just binning by 5 at the long wavelength to see things a little cleaner. And you can see that they all look pretty similar to each other, except for VE 169 up here at the top. And I think that's an interesting object, and it doesn't really look like any of the DISCO classes quite. So there's probably a lot more to be said about that one, but I'm going to exclude it and just move on and look at the ones that are similar to each other. And I'm throwing in the DISCO ones here as well, and of course there's a much nicer signal to noise down here because they're brighter. And you can see they're all very, very similar to each other. And I'll start pointing out some spectral features in a minute, but first what I want to do is show you some group averages. So this is actually the DISCO Cliff group split into 2 separate averages, and this is ongoing work that Rosario Brunetto is doing. You'll notice, if you've got good memory for spectral shapes, that those redder ones, not redder in terms of colors, just in terms of the color palette, here. Cliff 2 one looks very similar to what the spectra that I just showed you in the previous slide, all of these guys. And here's the average of all of the disco ones that were on that slide. And you can see that basically they're this Cliff 2 group. But now I'm going to show you the average of my sample, the ones that I have so far, which is generally smaller objects, higher H magnitudes. And they look very, very similar to this disco Cliff 2 up here, but they actually look sort of more like the Cliff 1s down here. And so that's maybe hinting at a kind of a surface veneer of one characteristic and something different below, because out here at these wavelengths, you're not seeing anywhere near as deep into the surface as you are here. So that's an interesting clue. I'm not sure what to make of it yet, but let's look at spectral features now. So what triggered all of this was the methanol on ASIAA, and they all have a blip of some sort there, but none of them are as deep as on ASIAA. So ASIAA is an oddball in terms of the methanol, assuming that's even methanol. Another thing that's kind of problematic with methanol is that methanol does have other absorptions throughout, just shy of 4 microns and in here. And those absorptions are not obvious here, but again, if we're not seeing very deep into the surface, and there's some surface veneer of perhaps radiolytically damaged material, maybe that's holding together, but we have to really do some modeling. All of them show carbon dioxide ice as well. You see the very weak carbon dioxide band here is present in all of them. The much, much stronger fundamental here, you don't see it in this one, which is the one that has the strongest carbon dioxide band there. And I think what might be just going on is that this whole continuum is much lower here, so there's something basically opaque across that whole wavelength range that's maybe suppressing it. Whereas you can see these ones sort of go up in albedo, and then that enables a band to be absorbed against that background. What else? Okay, so this is the CH stretch in organics, and most of them show something there, but this one's an oddball again. And finally, the color slopes are worth looking at. Every single one of them basically has a change in slope around maybe 1.2, 1.3 microns. And if you compare that to ASIAA does not do that. It bends over at maybe 1.5, 1.6 microns. And so there's also, again, an interesting difference there. Now, there's a lot of size range between ASIAA and my famous target. So if there's a size-dependent effect that kicks in around ASIAA's size, this sample won't really do a very good job of teasing that out. And one such phenomenon that might happen and do that is, if you think about the escape velocity, ASIAA's escape velocity is not very fast. And so micrometeorites basically kick stuff off and it's lost in space. Whereas a 100-kilometer object or a couple 100-kilometer object, micrometeorites kick off stuff, and a decent fraction of that doesn't escape to space. And so that could be a systematic difference where below some size you're in an erosion ability. Also, of course, if you're a large object, a couple 100 kilometers, you've got a much better chance of getting warm due to radiolytic decay earlier in the solar system history, especially if things form fast enough to get the really short half-life radioactive elements involved, which I suspect probably doesn't happen on the about, but anyway. So the next quick and dirty thing you can do is spectral indices, and these are really not the right thing to do. What we need to do is full up radius transfer models that count for the whole wavelength range. I haven't gotten around to that yet, but you can already see some trends. And I should point out that the white points are the ones that are in the slice, that controls for the H magnitude. So the white ones all have the same H magnitude. The gray ones are everything else. I included them, but you shouldn't use them to establish any trend because they're different in size. And the most maybe plausible trend is this increase in methanol, at least the methanol band, or what we call methanol in ASIAA. I don't know if it really is methanol, but it increases with heliocentric distance. That's ASIAA there. So is ASIAA basically looking like something that formed further in heliocentric distance because it's more erosional, or is it actually formed further away, or hard to say. There might be something going on with CO2 at the most distant object, but since it's only 1 point, I wouldn't push it. Water is really hard to pull out. This is the 2 micron band, but of course that's also OH, and I can't tell them apart, and there's enough other little bumps and wiggles that it really makes a huge difference where I put my boundaries for trying to calculate the spectral index. So I wouldn't really believe any of that. I think we will only really get quantitative water information out when we do the full-out modeling, because fortunately water has a lot of different absorption bands, and you can use all of that information when you do the modeling. So this is we couldn't bring myself to all these conclusions, but basically, I think there's some evidence of some trends with heliocentric distance, and I think we'll be able to tease that out when we get the rest of our observations and do some proper modeling. What it might end up being is that there are both size and distance dependencies mixed up together, and this sample at least has a chance to tease that out. And of course, like the previous talk, with the hot population, where you have yet another variable of not knowing where they formed, there's just too many variables. We just needed lots and lots and lots of spectra to actually tease all of these variables apart. But 3 more observations to go, and we'll complete this survey. And then I should also note that Susan Benanke has a color photometry survey that will get a couple more cold classicals, really small ones, and of course when there's JWST cycle 3 and cycle 4. So I'll leave it at that.
Well, I don't know how to ask this other than Michael, so I'll just ask it bluntly. Is it possible that the New Horizons central calibration isn't all that good?
It's always possible that you could do better with spectral calibration. However, we also use that instrument to look at things with much higher signal to noise, like Sharon, for instance, and it agrees pretty darn well. So I actually, some of the little bumps and wiggles that I was not willing to stick my neck out on the New Horizons Sharon data show up in the JWST data.
So another factor that's different with the New Horizons stuff is it is significantly higher phase.
Yes, although the Lisa data wasn't super duper high phase.
But it was still 10 degrees versus 0, basically. So it's going to make a difference.
Other questions?
Well, you suggested a few times that maybe the feature on air clouds might not be methanol. Do you have another idea for what it might be if it's not methanol?
Not really. So, what argues against it being methanol is the fact that we don't see some of the other methanol bands. And I think I'd feel more comfortable with some kind of layering effect to explain that than to go the other way around and say it's not methanol, it's something that looks like methanol, those same functional groups, but in some other setting, because it's just so hard to get them right in the exact same place.
Right. Thanks.
Thank you both.